All right, let's start. Good morning. So we still have the second fundamental theorem of calculus to discuss. So far we talked about how to integrate derivatives. This was FTC1. FTC2 is going to be the other way around. Namely, I want to differentiate an integral. So of course, in order for this to make sense, we're going to take at least one of the endpoints of this integral as the variable, and we're going to differentiate with respect to that. And so we're going to define that. And then once we're done with this, we're going to transition to Taylor approximation. And then we're going to be on our way to infinite series, infinite sums of numbers or functions. And that will be sort of the last topic of this course. OK. So I want to define this family of functions. If I take, as usual, I and a non-empty open interval, and a function on I, taking real values, that is locally hk integrable. In other words, on any closed and bounded subinterval of I, the restriction of f to that interval is hk integrable. That's what that means. So I'm defining this family of functions. F sub hk, comma bullets. Here, instead of having a sequence, I mean this is sort of like a parameter. So this family of functions is parameterized by points on the interval. For each gamma, there's a new function. So you should think of gamma as your initial condition, and f sub gamma is the function that satisfies that initial condition. OK, so like this. So this just means integrates f from gamma to x according to hk. Okay, and I'm calling this the hk cocycle, ultimately because of this exercise. But before going into that, of course, if I started with a Bourbaki, locally Bourbaki integrable function, whatever, I could have looked at different integrals according to the regularity of my function. These would give me different senses of cocycles like this. And the big exercise here is, well, if you have an a local hk integrable function for any 3 points, alpha, beta, gamma, you have this relationship. Integral from alpha to beta plus beta to gamma plus gamma to alpha should be 0. This is pretty much the same thing as saying that, how to say, if you have this configuration, this is saying that you can split your integral over subintervals and add them up. Okay. So, for instance, if you were to send this to the other side, this is integral from alpha to gamma of f plus integral from gamma to beta of f, and minus integral from alpha to beta of f. But certainly, if I were to change the endpoints, that would turn into a plus, and I can put this in the middle. Alpha to gamma, gamma to beta, beta to alpha. So this should be 0. This just says that this works, broadly speaking. I'm leaving this as an exercise because while it is important, it's an important equality, it's somewhat tedious to prove. So I'm going to leave it to you to sort of struggle through it. You can, I think, just take it for granted. I don't think it's very suspicious that this should hold. And indeed, in the problem set about sequence convergence, there was this problem about sort of discrete derivatives and discrete integrals of sequences. There was a similar sort of problem there too. The whole point here is that if you're adding from here to there and from here to there, it should equal the sum from here to there. So you should have this. So over loops like this, integrals should add up to 0. That's why you call it a cocycle. And this generally is called the cocycle identity. Okay. So I'm just going to go ahead and use this. So this should be my candidate for the integral I should differentiate. I should be able to differentiate. Ultimately, I would want to take one of these functions, say this, and then I should be able to differentiate this. Right, so maybe I should write it like this. Well, the derivative of this integral is the same thing as capital F sub hk gamma prime of x. Well, I would want this to be equal to lowercase f. That's what I would want. So we would like to be able to say things like, first of all, this guy is differentiable, this capital F. Okay? It turns out that even though this function that you start with is hk integrable or whatever, Bourbaki integrable, once you look at this antiderivative, or indefinite integral perhaps, let's say, or cocycle is the best way to say it, I think. In general, it's not true that this guy is differentiable. Okay, so we're going to have to think about that. So we're going to start with certain things that we can deduce regarding the regularity of this function. So for instance, we'll be able to say at the very least that if lowercase f is locally hk integrable, then this uppercase f, this hk cocycle, is always going to be continuous. Not necessarily differentiable, but it'll be continuous. Or we'll say if here we put r, so that we're looking at the Riemann integral cocycle of some Riemann integrable function, then we're going to see that this is automatically locally Lipschitz. Remember, local Lipschitz was something that was implied by C1 property, and this was for us pretty much this pretty much was for us a notion of weak differentiability. Okay, so in a sense, even though at large this cocycle may not be differentiable, at the very least we'll have that it is weakly differentiable and so on. So there's going to be certain complications about this. Now, first, before stating the second fundamental theorem, I want to go back to this local Lipschitz property, remind you what that was, and give a characterization of it so that we remind ourselves. So I want to say this, claim. Let me look at my notation. Okay. So let G be a function on my open non-empty interval. Then I can say this. Then G is locally Lipschitz if and only if it is Lipschitz on each closed and bounded subinterval. if and only if for each compact subinterval k in I, G restricted to k is Lipschitz. Now, what was the Lipschitz property and local Lipschitz property? G is Lipschitz on whatever subset. I'll leave it like this. If there's a constant such that for any 2 points in your interval, well, the distance between the outputs is dominated up to this constant c by the distance between the inputs. In other words, g of x1 minus g of x2 in absolute value is upper bounded by c times x1 minus x2. Okay. In other words, taking this to the other side as a division, this says that I have a control over rise over run. And that's why we said this local Lipschitz or this Lipschitz property is something like a weak differentiability property. I have some control over rise over run. And then what is local Lipschitz? Well, local Lipschitz is when you have a function that is not Lipschitz at large necessarily, but as a given any point, there is a neighborhood of that point. There's an open interval centered at that point, or rather maybe I should say closed interval, not that it matters that much, such that when you restrict your function to that subinterval, then it is Lipschitz. Okay. For any x star in I, there is a delta that in principle depends on x star, so it's a gauge if you want, such that g restricted to x star minus delta, x star plus delta is Lipschitz. That was how we defined local Lipschitz property. And then we had shown that if g is C1, that is to say, if g is continuously differentiable, and its derivative is continuous also, then it is local Lipschitz. And we said, oh, g being C1 means it is differentiable in the strong sense, and we would expect that strong differentiability implies weak differentiability. Okay? But on the other hand, so we sort of like started defining certain properties in the local sense, right? I was talking about you take this property and how do you define a function or whatever having the same property locally. We sort of, for instance, defined local minima, local maxima, whatever, using the same idea. But then when we transition to integral calculus, or when we try to fold bring integral calculus back into the fold, I also used a notion of localness for integrability, for instance here, local integrability. But for local integrability, instead of choosing this base point and then an open interval, whatever, how I defined this was, I said, well, f is locally integrable if it is integrable on each closed and bounded subinterval. Okay? Here. So the notion of local here that allowed us to modify Lipschitz property to the local Lipschitz property that is more within the realm of differential calculus. Within the realm of integral calculus, a local property is something that you have on closed and bounded subintervals. So f from I to R is locally integrable relative to whichever sense you're looking into, if it is integrable on each closed and bounded subinterval. It is integrable on each compact subinterval. Okay? Now, in principle, this compact subinterval need not be a small subinterval. It could be very large. If you started with I, the whole reals, maybe your compact subinterval is, so if I were the whole reals, your compact subinterval could be, in principle, minus 10 to the 10 to the 10 to the 10, and then 10 to the 10 to the 10 to the 10. Okay? So that's sort of like a valid compact subinterval. I'm not mentioning anything about how long, how large the interval should be. But you see, this claim really connects the two senses of local properties. Localness in the sense of differential calculus, localness in the sense of integral calculus. Well, it says, in fact, Lipschitz property is, somehow right in between. So you can take Lipschitz property, localize it, think of it as a local property in the differential calculus sense, or you can think of it as a local property in the integral calculus sense. These are equivalent. Okay? So that is what is at stake here. When we transition to the second fundamental theorem of calculus, I'm going to use this word. But in principle, we could have just used this version also. Okay? Any comments or questions so far? And this will be a nice review of some of the methods, earlier methods that we discussed in this class. It has been a while since we've taken sequences and stuff, so I thought it would be good to remind ourselves. So here's the proof. It's an equivalent, so I need to prove it both ways. Okay. Let's see. One of the sides is slightly easier. Okay. I think this side is easier. I'm assuming that g is some function such that on each compact subinterval, its restriction to that compact subinterval is Lipschitz. And I want to show that it is locally Lipschitz. So I need to let a point x star in I, okay? I need to show that this x star has some neighborhood such that on it, g is locally Lipschitz. Well, I is an open interval, which means that there is some delta such that x star minus delta, x star plus delta is within I. Okay. But then, if I were to halve this delta, I could for sure say that the closed and bounded interval from x star minus delta over 2 to x star plus delta over 2 is completely within I. certain that this is a closed and bounded subinterval. So I can call it K, by the hypothesis that G is Lipschitz on each compact subinterval. I know that there is some constant C. So by hypothesis, there is a constant C that in principle depends on K actually, but never mind. Such that for any x1, x2 in K, I have the Lipschitz condition, bound over rise over run. Okay. Well, if this is true, then if I were to get rid of the endpoints of this, I would have an open interval, right, centered at x star of some radius. And that would be my open interval here. Hence, this is Lipschitz. And so ultimately, for each x star, I was able to find an open interval containing it, such that G restricted to it is Lipschitz. That's what it means for G to be locally Lipschitz. Okay? This is one side. The other side is slightly harder. Comments or questions about this so far? Hmm?
So when you want to prove the claim, right?
Yes.
Which is if and only if.
Yes.
Right? So we start out from the lower part,
Yes.
go up there.
Yes.
And by hypothesis, which hypothesis?
Hypothesis is the statement. Yes. Yeah, so at this point, I'm not writing this explicitly, but since I'm going in this direction, the hypothesis is, well, G is a function from I to R, and on each compact subinterval, G restricted to K is Lipschitz. That's the hypothesis. Make sense? Because I was going in this direction. Okay. Now we need to go the other way around. It's slightly harder, I think. For the other way around, I want to assume, so I want to prove that local Lipschitz property implies that G restricted to any compact subinterval is Lipschitz. Okay. I can go for a contradiction. So suppose G is locally Lipschitz, but it is not the case that on each compact subinterval, G restricted to K is Lipschitz. How do you negate this? You say, oh, G is locally Lipschitz. However, there is some compact subinterval K such that G restricted to it is not Lipschitz. That's how you negate it. I think I'll erase this part. Okay. So for this direction, suppose for a contradiction that G is locally Lipschitz, but there is a compact subinterval. It could be multiple, but for contradiction, I can only assume one. There is a compact subinterval k and I such that G restricted to k fails to be Lipschitz, is not Lipschitz. Okay. Now what does it mean for G restricted to k to be not Lipschitz? Well, we need to negate again. So how do you do this? Well, let's remind ourselves. We can just write down the condition for Lipschitz property and then negate it carefully. So Lipschitz property is there's a constant c such that for any xy in k, g of x minus g of y in absolute value is upper bounded by c times x minus y. That's Lipschitz property. Not Lipschitz property is its negation. Okay. That is to say, its negation turns into this. For any c, there are two numbers, 2 points, x and y in k, such that the distance between their images is lower bounded by c times the distance between the inputs. For any c, there are 2 points x and y, such that g of x minus g of y in absolute value is strictly greater than c times x minus y in absolute value. Okay. Now I should ask you, how can I move forward from this? I have the local Lipschitz property. And I should mention this as well. Local Lipschitz property implies automatically that your function is continuous. Okay, I'll write it here in case it's not clear that much, because it's an important property. This was an exercise that I gave when I first defined local Lipschitz property, but let's mention it again explicitly because it's important. So weakly differentiable, right? Local Lipschitz means weakly differentiable. Certainly weakly differentiable, I mean, it's reasonable to expect that weakly differentiable implies continuous. That's not always true, but in this case it is. So I'll write it here. So remark perhaps. Local Lipschitz property implies continuous. Okay? Why is that? Well, in order for G to be local Lipschitz, it has to be the case that for any x, there's a delta such that, and there's a constant such that for any 2 points, delta close to x star, the distance between their outputs under G is upper bounded by c times the distance between them. But then instead of choosing 2 points that are delta close to x star, I can just choose one of the points to be x star itself, because certainly x star is delta close to itself. Therefore, what I can say is, for any x star, there's a delta and there's a constant such that for any x, if x minus x star is within a delta, then g of x minus g of x star is upper bounded by c times this. Okay? Local Lipschitz property implies this. Well, if that is the case, for any epsilon, okay, I can choose delta, right? So this is what I want to be upper bounded by epsilon. Once I fix x star and epsilon, there is some delta, but then I can adjust that delta to let's say, delta bar, say, which is going to be the min of this delta, and so if I want this to be upper bounded by epsilon, I would want it to be less than epsilon divided by c. That's still a positive number. And if x is delta bar close to x star, this is going to be bounded by epsilon, which means the output is going to be bounded by epsilon also. All this is to say local Lipschitz implies continuous. Okay? This is, I'm sort of like fast forwarding this argument, but this is a really nice argument. I think it would be very good to go over it if it's not super clear. Okay, but that's how you prove it ultimately. In any event, going back to this, local Lipschitz is going to imply continuous. That's all we need for now, for this part. So somehow, I want to use this continuity property of G. And I have this property. How can I move forward? And remember, I started with assuming the negation of what I'm trying to prove. So I want to get a contradiction. How can I sort of get a contradiction from this situation? There's pretty much one method that we use quite a bit in this kind of a situation. For any C, positive number, there are 2 points in my set. What can I do here? This was a method that we kept using during sequences. For instance, the first time we used the method I'm thinking of, well, we used it for the first time when we were trying to show that the continuity, the epsilon delta definition of continuity is equivalent to the sequence definition of continuity. I'll give you a couple of minutes. It's good to try to remember. So I have that G is locally Lipschitz and therefore continuous by the remark. But there is some compact subinterval, which I'm going to fix for the rest of the proof, K, such that restricted to this K, G is not Lipschitz, which ultimately boils down to this statement. For any C, there are 2 points in K, such that something happens. Well, it says for any C, okay? What I can do is I can leverage that for any C, something happens by choosing larger and larger C's. That would help me separate G of x and G of y in a sequential manner. Right? So this was the idea of the farming. I'm just going to farm this statement. Okay? Say C is 1. This was the idea that I was mentioning. I'm going to come up with a sequence. So if I choose C to be, for instance, 1, 2, 3, whatever, well, for each choice of C, I'm going to have 1x and 1y. So that's going to generate for me a sequence, or 2 sequences in K. Okay? So say, for instance, C equals 1. Okay? For C equals 1, this should hold. Therefore, there is some x1 and y1 that satisfies this property. Okay. Now, in principle, I wrote the same thing. y1, okay. So this is all I have for now, okay? But I want to do the same thing and keep sort of separating this left-hand side to be larger and larger. I want to make it so that for each choice of x and y, the gap between g of x and g of y are separated, so that I would know for sure that the image doesn't converge, okay? Now I want to do something like this. Say, for instance, I can take C to be the max of 2. Is that what I want to do? So the trick here is I need to choose my C's in a sequential manner in such a way that this side, this lower bound, keeps increasing for sure. Okay, I think what I can do is this. Let's think about it slowly. This I have. Now, this expression is lower bounded by 0 because it's an absolute value. On the other hand, it is upper bounded by this. If it were the case that x1 equals y1, that would tell me that this is 0, okay? But on the other hand, this too would be 0, because it would be g of x1 minus g of the same point. Therefore, this would be 0, and that would give a contradiction. Therefore, this implies that x1 is not the same point as y1, for instance. Okay. Consequently, this is a positive number. Okay. For my next choice of C, I want to engineer that second choice in such a way that this gap is even larger. Okay. So let's try to figure this out here. So I'm going to choose another C, and it's going to give me, by farming this, 2 points x2 and y2, but I want the choice of C to be so that this is lower bounded by something that is even larger in a sense. X2, y2. It's basic arithmetic at this point, but I'm kind of choking right now, trying to figure out. So this was the case when C equals 1. Ultimately, I want whatever is here. There's going to be something here. I want this to be even larger than this guy. And in fact, maybe twice this. But certainly, this is going to be lower bounded by C times x2, y2. The problem here is that I don't quite have explicit control over x2 and y2. This is just an existential statement. I have only control over C. Once I choose a C, x2 and y2 are going to be given to me, but it might, so what I'm trying to handle here is, I might try to choose the C to be large enough, 10 billion, whatever. But that doesn't guarantee that these are very small, such that ultimately there's compensation here, and this becomes very small. I don't want that to happen. But ultimately, I want this to be like this. How can I? So if I choose C something like 2, for instance, let's just write it for now. I don't think this is going to work, but let's try to figure it out. If I were to choose C to be 2, then that would give me 2 points, x2 and y2, such that this happens. Is upper bounded by 2 times x2 minus y2. Again, by the same argument as before, I can say that this is positive. They cannot be the same point, because otherwise this would be 0. And this is strict inequality. So it's a positive number. You see, the problem here is I really want, so this, going this way, that I would get 2 sequences, x bullet and y bullet in K. Yeah, let's try to finish this proof this way. It's not going to probably work, but we can perhaps adjust it so that it works. So by induction, there are 2 sequences in K such that for any n positive, this happens. That's what farming would give me if I were to just keep choosing C to be integers. My idea here was something like this. Once I have this situation, I have 2 sequences in this closed and bounded subinterval. Then I can apply Bolzano-Weierstrass to these to get a convergent subsequence for each of them. So I can just assume that these actually converge to some places. This guy up to a subsequence, but let's not worry about it. It converges to something in K. Y bullet converges to something in K also. There was a little trick here that came up later. Let me see. I think as I was thinking about this, I convinced myself that this works somehow. I can fix this. It's just that I don't quite remember at this point how I fixed it. Well, I can certainly say at this point, let's try to figure this out. This is like a good review. This converges to this point. This converges to this point. Therefore, this converges to g of x infinity minus y of g of y infinity by the continuity of g. So this is a finite. This converges to a finite number. In order for this to converge to a finite number, the only way that can happen is, well, because this blows up, otherwise, unless this is 0, this converges to 0, faster than n does, in fact, it must be the case that x infinity is the same thing as y infinity. Yeah, let's see where this takes us. G and absolute values, whatever, limit as n goes to infinity of g of xn minus g of yn, an absolute value, this exists, is equal to g of x infinity minus g of y infinity, an absolute value, which is a finite number. Therefore, since this sequence, parameterized by n, is squeezed between two things that converge, ultimately this has to converge also, or at the very least, it should be a bounded sequence. The only way that can happen, because this blows up, is if these go to 0. In other words, x infinity, in fact, is the same point as y infinity. Oh, OK. OK, now it works. OK, that's fine. That was, OK, good. It works. OK, apologies for this. Let me just backtrack and try to explain to you why this actually works. So back to here. OK, I just negated the statement that G restricted to K is not Lipschitz. I wrote down the definition of what it means for G restricted to K to be Lipschitz, negated it, I get this. Now I'm going to farm this using different choices for C. OK, I just choose C equals 1, C equals 2, whatever. That gives me two sequences in K with the special property that for any integer n, the distance between their images is lower bounded by n times x sub n minus y sub n in absolute value. This part is fine. I'll try to be a little bit more explicit here. OK, now here's the main trick again. An important thing, I have two sequences in some closed and bounded subset. OK, the only thing I know here is Bolzano-Weierstrass. Remember, Bolzano-Weierstrass allows me to extract a subsequence that converges. OK, initially I assume that these themselves converge, but in principle you should be choosing a subsequence. OK, so maybe I'll write that down too to remind you. There's a j, sort of strictly increasing function, such that there's a j and x infinity bar, let's say. In K, such that this specific subsequence converges to this. Applying Bolzano-Weierstrass to this specific subsequence of the other sequence, I need to synchronize the times. Because you see, I can only compare x bullet and y bullet at the same time. So that's sort of a trick. By Bolzano-Weierstrass applied to y bullet composed with j, I have another strictly increasing function k and a limit y infinity bar in k such that y bullet composed with j composed with k converges to y infinity bar. But since x bullet composed with j converges to this, so does x bullet composed with j composed with k. And then we're going to basically finish the proof this way. Unfortunately, I'm out of time. I apologize for choking here, but we're going to continue this, doing this tomorrow. Thank you. Okay, let's start. Good morning. I'm going to take attendance today. So the grades for the second midterm is up. I'm generally happy. I put the key on Canvas as well. I would highly recommend that for the final you do study my solutions, compare your solutions to it. Just to say a couple words. So this example in the midterm was, it looked like this. So it has a bunch of spikes like so. This was the function that was given to you. Okay. So this, in fact, is an example of a Riemann integrable function that is not Bourbaki integrable. Some of you confused the definition of Bourbaki integrability. Bourbaki integrability is about whether or not you can approximate a function using sequences of step functions uniformly. Okay. So one part of the problem is, can you approximate this using steps pointwise? That is true. You can approximate this pointwise. Just imagine these tines, right? Start sort of adding one at a time. So this is your first step function. Then add the second tine like this. And then add the third tine. Okay. This is a sequence of steps. Just to verify, any such function takes exactly two values, so the image is finite. Given any value in the image, what is the level set? It's either finitely many points, union of finitely many points. Points are intervals for us, right? So this set that contains only 0, you can think of it as this. Remember, when we were doing like integrals and stuff, I always wrote lambda to rho closed, lambda less than or equal to rho. So it is allowed. So these are step functions, and they converge pointwise to this function f. However, there is no sequence of step functions that converges to f uniformly. Okay. So I wrote the detailed solution in the key, but the main idea is this. The reason why there is no such step function is because these tines for f, they accumulate at a point. They accumulate to 1. And so we're going to say, if I have a step function, it can have at most finitely many discontinuities, which means there's going to be some point somewhere here, let's say, such that my step function is going to be constant after it. Maybe there's a discontinuity for my step function here, but there's going to be sort of like the maximum value like this. So there's going to be some piece in the graph of the step function that I'm trying to use to approximate f, such that it's going to look like this. But if that is the case, and if I'm trying to approximate f using the step function uniformly, well, it better be the case that this little piece is close to these pieces, but simultaneous to these pieces. And in fact, what you can show, and that's what I did, is for any sigma step, the C0 distance between f and sigma is lower bounded by 1/2. So in the best possible situation, this last piece is sort of right in between. But if any step function is at most, or at least 1/2 away from f, that means that you cannot approximate it using steps uniformly. Okay, not pointwise. Pointwise is fine. And Bourbaki integrability here was all about uniform approximation. So this is Riemann integrable, but not Bourbaki. Okay. It's a good point. Another thing I wanted to mention, there was this tricky problem toward the end. It says, well, there are two tricky problems, I think. One of them was about the statement that if you have a function f on a closed and bounded interval, whose absolute value function is Riemann integrable, then the function too is Riemann integrable. So this was asking the other way around. So we have that if f is Riemann integrable, then so is f in absolute value. But this is not necessarily, this doesn't necessarily work the other way around. So for instance, the simplest example is this, right? So I want to come up with an f that is very bad. I want f to be bad, but f in absolute value, really nice. Well, imagine f is a function whose absolute value is always 1. Okay? We can come up with a function that perhaps oscillates between 1 and -1, but if you make f oscillate too much, then you can break integrability. That's the main idea. So for instance, what you can do is, so this is 0, 1, this is 1, this is -1. Right? So say f of x is 1 if x is a rational point, and -1 otherwise, between 0 and 1, let's say. The absolute value of this function is just a function that is constantly 1. Certainly it is integrable, but this guy is not integrable. We had shown in class one side of this, right? So this is, so if I were to call g of x to be 1 if x is in Q, 0 otherwise, we had shown in class that this function is not Riemann integrable, even though it is HK integrable. Well, certainly this is nothing but, I can write it perhaps like this. Right, so f is g minus, I think 1 minus g. Yeah. Yeah, so this 1 minus g is nothing but the function that is 1 on irrational points and 0 otherwise. So this part is this part is this. If I take their linear combination, that's going to give me f. And this is not Riemann integrable. You can show that its upper Riemann integral is 1, lower Riemann integral is -1. So the Darby aperture for this function is 2, for instance, for any partition. Lower bounded by 2. So that was one example. And in fact, this came from the textbook. It was one of the few problems about the integration theory that I had liked from the textbook. So that was that. Kind of a tricky problem. The final tricky problem was a differentiation problem, the quotient rule. So I'll do it here. So we were given that f and g are two functions. And we're just looking at differentiability at 0. We're assuming that both of these are differentiable at 0. And we're assuming that g of 0 is not 0. In the first part, I was asking, you to verify that this ratio function is well defined as a function taking real values and some interval containing 0. The point here is this. I want to say something about the differentiability of this ratio function at the origin. But by definition, in order for that to even work, it has to be the case that this function is well defined in an interval containing the origin, because we talked about differentiability of a function insofar as that function is defined on an open interval. So I need to first say that this function is well defined on an open interval. I was expecting something like this. Because g is differentiable and g of 0 is 0, well, differentiability at 0 implies that g is continuous at 0. And then I was expecting you to say something along the lines of, oh, because g is continuous at 0 and it is not 0 itself, well, there is some neighborhood of 0 such that on that neighborhood, g is still non-zero. We had used a similar argument in one of the proofs earlier. I was expecting you to say something like that. So that was the first part. In the second part, I was asking you to verify establish the quotient rule. Some of you tried to use this big O stuff or little o stuff, and you got stuck because it's somewhat tricky to use little o in that situation. Ratios are somewhat hard to use with little o. I think the easiest way is to just use some sort of a chain rule type of thing. So I defined phi of x to be the reciprocal function 1 over x. Then f divided by g is nothing but f multiplied by phi composed with g. And then you apply first the product rule to this, and then the chain rule to this to recover the formula. That's, I think, the easiest way to recover this. Okay. You can go ahead and sort of read the details and the key, but I just wanted to mention all these things. Any comments or questions about the midterm and how it was graded? Or do you have any feedback? I hope it was better than last time. Yeah. Yeah, I mean, it's as far as I'm concerned, your performance in the midterm says very little about what you can actually do in terms of math and how much you understood and stuff. Because somewhat of a, forced environment, time constraints and stuff like that. But we are supposed to give in-class midterms, so that's sort of the midway. If I had more flexibility, I probably would give like a take-home, but then that would be like rather brutal. Okay. So that's that. Now I want to finish the discussion of this result, this claim that I was discussing yesterday that I messed up the proof of yesterday. So what I said yesterday, ultimately what I figured out does work. I'm just going to take my time, write it out again, just so that we have we do some review over continuity and Bolzano-Weierstrass, subsequences, all these things. And then we're going to state the second fundamental theorem of calculus. It's going to have 10 items. That's how I decided to state it. But somehow, compared to FTC1, many of the items that look rather different, well, they don't look very different, but many of the items have like very straightforward proofs that work for multiple items. And some of them, again, I'm going to leave to you. There's one contentious part that we may end up skipping. So yeah, so we're going to do the proof of this claim. Then FTC2, statement and proof, hopefully. Then I want to switch over to Taylor approximation, but probably even before that, we should say a couple words about some of the nice computational tools in terms of the joining of integral and differential calculus. One of them should be something like a u-substitution, change of variables formula. And another one probably should be like integration by parts. There are like many versions of these, but probably I'm going to just keep it simple and just give the most baby versions of these. baby u sub, baby by parts. Okay. And then probably that will be it for today. I do want to state and finish the proof of Taylor approximation by the end of this week so that we can safely discuss series and stuff. Because next week too, what I'm planning to do is this. So according to plan, next week we're going to start talking about infinite sums, in other words, series. If you had seen these before, I just said these are nothing but specialized types of sequences. So if you have a sequence, you can just look at the sequence of partial sums. The limit of that sequence of partial sums is nothing but the series. So there is nothing fundamentally different compared to the things that we discussed, but there are certain sort of extra statements that relate the convergence of this infinite series to certain properties of the term sequence. Okay, so we're going to have to discuss that. And one of the things that we had mentioned, but I skipped back in the day when we were discussing sequences of reals or functions, whatever, was this property of Cauchy sequences. Now, when it comes to series, infinite sums, this Cauchy property does end up being rather useful. So I think what I'm going to do next week is I'm going to also take my time, go back and do some of the statements or some of the theorems that we skipped back in the day, just so that we remember, because Cauchy property is also rather important. And then we're going to be on our way. Okay, so the claim was this. I, as usual, is a non-empty open interval, and I take one function g on I, taking real values. And the claim is g is locally Lipschitz if and only if on each compact subinterval k of I, the restriction of g to k is Lipschitz. Now, I wrote here, instead of subinterval, you can just use subset too if you want. Subset, compact subset means any sequence in K has a subsequence that converges to some point in K. So the definition of a compact subset is literally something on which Bolzano-Weierstrass works automatically. You just axiomatize Bolzano-Weierstrass, and that's the notion of compactness. I'm just going to stick to the subinterval case, of course, but the same argument actually works for subsets. And I wanted to mention this as well. It's a nice exercise. I'm not even defining what it means for a function to be locally bounded, but part of the exercise is for you to define it. At this point, you should know how to define what it means for a function to be locally bounded. In much the same fashion as this claim, a function is locally bounded if and only if on each compact subinterval k, its restriction is bounded. Okay, these are sort of like symmetric. And what was the main idea behind these two? Well, this local property stated this way is sort of localness in the sense of differential calculus. Any point has a neighborhood such that whatever happens. On the other hand, the second condition is localness in the sense of integral calculus. And this claim says Lipschitz property, when you're trying to localize it, it doesn't matter whether or not you're localizing it relative to the differential calculus approach or relative to the integral calculus approach. And there's a similar thing happening for localizing the property of boundedness. Okay. Okay. So, proof of claim. Yesterday we had successfully proved that if I have a function g such that the restriction of it is Lipschitz on each closed and bounded subinterval, then the function is locally Lipschitz. So that was this side. For the other side, I'm going to go ahead and write everything again. So say I have a local Lipschitz function. And remember, local Lipschitz implies C0. Continuous. It also implies locally bounded, by the way. Never mind, we're not going to use that. And for a contradiction, I'm going to assume that the other condition doesn't work. In other words, there's at least one compact subinterval k such that g restricted to it is not Lipschitz. Compact subinterval K such that G restricted to K is not Lipschitz. So on this compact subinterval, there is no control for the rise over run for G. Right? Writing this out explicitly, we figured out that this is the same thing as saying for any C positive, there are 2 points x and y in K such that the distance between their images is lower bounded by C times the distance between these 2 points. So g of x minus g of y in absolute value, that's the distance between the images. Well, this upper bounds C times x minus y in absolute value. Okay? And then we took this statement, farmed it using an increasing sequence. In this case, we just use integers. If I were to choose C to be running from running over positive integers, I have 2 sequences then. So there is 2 sequences, x bullet and y bullet in K, such that for any n positive, g of x sub n minus g of y sub n is lower bounded by n times x sub n minus y sub n in absolute value. Okay. And in fact, what I can say here is for no n is x sub n at the same point as y sub n. Because if x sub n were the same thing as y sub n for some n, well, this would be 0, but then this would be 0. But there's no way, oh, I should say it like this. This would be 0, but then this would be a non-negative number, strictly less than 0. That cannot happen. Therefore, this is lower bounded by 0. Okay. Now, K being a compact interval is the same thing as saying that it's a closed and bounded interval. Therefore, x bullet and y bullet are both bounded sequences. The only thing we can use, or the main thing we use for bounded sequences, is Bolzano-Weierstrass. Bolzano-Weierstrass allows us to pass to a subsequence of this so that it converges. Okay? There could be multiple subsequences of this that converge to different points in principle. And likewise for this. But somehow I need to synchronize these subsequences because ultimately I want to use this statement. And this statement allows me to compare what is happening according to x bullet and what is happening according to y bullet insofar as I'm comparing what is happening at the same time. So I need to synchronize these two subsequences that I'm going to use for Bolzano-Weierstrass. Okay. By Bolzano-Weierstrass, there is a strictly increasing function j from positive integers to itself, and some point x bar infinity in K, such that x bullet composed with j converges to x bar infinity. Okay, just so that I can synchronize the times I'm sampling out. Now, instead of applying Bolzano-Weierstrass to this y bullet, this other sequence, I'm going to apply Bolzano-Weierstrass to y bullet composed with this specific time change, or a subsequence function. I guess it's a good name to call this a time change, actually. I'll write it here. by Bolzano-Weierstrass applied to y bullet composed with j, this itself has a subsequence that converges. There's another strictly increasing function of positive integers and some limit point in k such that y bullet composed with j composed with k converges to y infinity bar. But then, since x bullet composed with j converges to x infinity bar, any further subsequence of this is still going to converge to the same point. Which means if I were to pass to the corresponding subsequence, this subsequence of x bullet composed with j still is going to converge to the same limit. Okay. Now, just to reiterate, what would this mean? Limit as n goes to infinity of x sub j of k of n minus x sub infinity bar in absolute value is 0. This is just the shorthand of writing this. And likewise this. I should also mention, even though I did this explicitly this time, at this point I think it's safe to just fast forward all this Bolzano-Weierstrass arguments. So instead of writing all this stuff explicitly, you can say there are two blah, blah, blah. At this point, you can say, without loss of generality, we can assume that these two sequences converge. Okay. Or log, we may assume x bullet and y bullet converge. That's a perfectly valid way to fast forward these arguments. Okay, like you would almost never see these subsequences written out explicitly. Yes.
And what would say they converge to the same?
At this point, I don't know if they converge to the same point. We're going to argue for that. At this point, I know that this subsequence converges to one point in k, and likewise, this other subsequence of the other sequence converges to some other point. But the next step is going to be to argue for the statement that this limit is the same thing as this limit, in fact. Okay? Now, any other questions up to here? So I have two convergent sequences in K. Now I want to use the conclusion from local Lipschitz assumption that G is continuous. Because G is continuous, I know that G applied to this is going to converge to the G of this, and likewise for this guy. And consequently, this expression is going to converge to some number. Okay? I'll write it like this. Limit as n goes to infinity of g of x sub j composed with k of n minus g of y sub j composed with k of n in absolute value it converges to a finite real number. Is convergence. Well, I'll just write it like this. Is equal to L, which is a finite number. Okay, this limit exists. Okay. But if that is the case, because for each term of x bullet and y bullet, if I'm comparing x bullet and y bullet at the same time, well, I'm going to have a bound like this. And since in this expression, this converges as n goes to infinity, j of k of n is going to go to infinity because both j and k are strictly increasing. Therefore, the only way this can happen is if this expression for these subsequences goes to 0, in fact. I'll write it like this. This is the important property. Okay. Hence, by red star, limit as n goes to infinity of this expression is 0. Okay. So in fact, you can say, oh, since, okay, if that is the case, since this goes to infinity, the only way this product can go to 0 is if this goes to 0, in fact, faster than this goes to infinity. Consequently, the limit of this has to equal to the limit of this. And in fact, what I can write is I can come up with a bound on this distance. Namely, this should decay faster than this grows. In other words, this should be little o of the reciprocal of this. As n goes to infinity. We're not going to use this, but it's good to write it. So this is j of y sub j of k of n plus little o of 1 over j of k of n as n goes to infinity. I can perfectly write this. Okay. Just a review. Not that we're going to use it. Now, the only hypothesis that I haven't used is really the fact that G is locally Lipschitz. So far, I only use that it is continuous. But now I want to use the local Lipschitz property. I'm going to apply local Lipschitz property of G to a neighborhood of this. By the local Lipschitz hypothesis, well, there's a delta such that G restricted to the delta neighborhood of this limit point is Lipschitz. There's a C such that for any xy in I, if x is delta close and y is delta close to the same point, then g of x minus g of y is upper bounded by c times x minus y in absolute value. I just use the fact that g is locally Lipschitz. So in some neighborhood of this limit point, it has to be Lipschitz. There's some constant positive. Okay? But then, since both of these sequences converge to the same point, I know that if I wait finite time, both of these terms are going to be within a delta. Okay? something's going to happen. Let's put here a dagger. Continue on here. This such that this is at most delta, and likewise y is going to be delta close to the limit point, which means I can apply this to the terms, but then combining it with this, I have this. Like so, and then this is upper bounded by c times, no, this is, this upper bounds this, which then, by the Lipschitz, local Lipschitz property, is upper bounded by c times this distance. Okay, so what I'm saying ultimately is that there is a finite number, and there's an uppercase n, such that after it, I have that this is upper bounded by this. But however, you see, this is always positive. This is at least 1. Therefore, in order for this product to be positive, it must be the case that this is positive. But then I'm saying I have some positive number here. Positive number times positive number is upper bounded by c times the same positive number. Therefore, I can cancel this with this, which then gives me that for any lowercase n after this uppercase n, this is upper bounded by c. That's a contradiction, because I can take lowercase n to infinity, in which case this is going to go to infinity, but I'm saying simultaneously that it is bounded. That's a contradiction. And the end of the proof. Took longer than I thought, but I think it was a good idea to do some review like this. So technically, we're not using anything specific to differential calculus nor integral calculus. I could have defined local Lipschitz property and so on back in week 3 or 4. But you see how now continuity gets sort of integrated into the theory. Okay. Any comments or questions about this proof? There are, by the way, much easier proofs of this, but that requires sort of really understanding what it means for a set to be compact. There's a characterization of what it means for a set to be compact that is much more convenient in this context. Using that is like a 2-line proof, but since you don't have access to it, it takes longer to write down. Okay, so that's that. And I think with this, and with the remaining 10 minutes, I can start stating the fundamental theorem of calculus 2. I'll leave this. I'll start stating it here. In fact, I'll I'll take a shortcut and state only part of it, because probably we're not going to be able to prove every single item that I had listed. Second fundamental theorem of calculus is going to be about the derivative of integrals. Remember, we had these functions. We had lowercase f integrable, or rather locally integrable, relative to some integration theory. And then we choose one point. This is going to be our initial condition. Then I can just look at the integral of lowercase f, starting from gamma all the way up to x, and x is going to be my variable for the new function. And so depending on which integration theory we mean, here f could be hk integrable, in which case we would take hk integrals and so on. But depending on the integration theory, you have different sort of functions, families of functions like this. And yesterday I called this the hk cocycle or whatever. B, R, L, hk integral cocycle if you want. Then we have this wonderful property that you have this if you keep sort of changing the endpoints in a cyclic manner and keep adding them up, you're going to end up zero. You're going to end up at 0. Gamma to alpha is 0. This was a wonderful property that we were using. Well, I want to say something like this then. If I have a locally integrable function, lowercase f, then this should be at least continuous. That is certainly true. Okay? So let's perhaps say it like this. I'll state it for Riemann integrals, actually. There will be 10 items, according to what I wrote here, but this is one of the items. For any locally Riemann integrable function, and for any gamma in I look at this using Riemann integrals. I want to say that the associated cocycle function, in fact, is local Lipschitz. In other words, not only is this continuous in x, but furthermore, it is weakly differentiable. Remember, local Lipschitz means weakly differentiable. Okay. Let's try to start writing the proof. It's not very sophisticated of a proof. What do I need to control? Let's not worry about, deltas, whatever. Start from the end. What you're trying to control? Well, I'm trying to control an expression of the following form. I'm going to choose an x star in I, and I want to say if h is small enough in absolute value, then this is upper bounded by a constant times h in absolute value. This is what I want. Okay. So I want to look at this, and I want to try to rearrange it. I'll do this once, slowly. The main idea here, you can expand these integrals and write them like this as well, but I find it a lot more convenient to just use the cocycle identity. Okay. So for instance, in the cocycle identity, it doesn't say anything about alpha, beta, and gamma being distinct. So if I were to choose all 3 points to be the same, f sub alpha of alpha is 0, which means I can choose alpha, beta, beta, alpha, alpha, alpha. That would give me that if I were to flip these two, I would pick up a plus. Okay. Again, by the cocycle identity, if you have x star to gamma, gamma to x star plus h, the sum is the same thing as f sub x star plus h. You don't have to write all this, but ultimately what this means is this is the integral from x star to x star plus h of f. But then if that is the case, I can just take the absolute values of these. Boop, 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 boop. And I know that for Riemann integrals, at the very least, I can take the absolute value inside. But then, for h small, since I know that f is locally Riemann integrable, it is Riemann integrable on a compact subinterval containing this. And on it, it has to be bounded. Therefore, that means that this is upper bounded by something. Say the upper bound is m or c here. This is upper bounded by c. So this integral is upper bounded by the integral of c from here to there, in which case that integral just ends up being this. Okay. Literally the same proof works for b integrals, Bourbaki integrals, because Bourbaki integrals has this property as well. This idea doesn't quite work for HK integrals, but there's a similar argument that we're going to be able to make. So that's one part of FTC2. Insofar as you can integrate something, this function is going to be at least continuous. Okay? But we want to go further. We would like to be able to say that under certain circumstances, this function, in fact, is an antiderivative of lowercase f, because ultimately we want to differentiate this. And indeed, if it is the case that lowercase f is continuous, then uppercase f is going to be differentiable with derivative equals to this. Okay. Do I want to start? I have a couple minutes. I'll try to write some stuff, actually. We're going to spend more time tomorrow on this. So if I start with an integrable function, lowercase f, then this uppercase f is going to be at least continuous. That's the first part of FTC2. FTC2 continued. If I start with a continuous function, then for any gamma, I want this to be a differentiable, and I want its derivative to be lowercase f. Consequently, this would imply that any continuous function, for instance, is Newton integrable. Because I'm saying, if you start with a continuous function, this is going to be an antiderivative of the function that you started with. It certainly is not the case that any Newton integrable is continuous, however. Okay. All right, I think I don't want to push any further. It's a good place to stop. We're going to continue tomorrow with the the nice statement of etc2 and various proofs. Thank you. All right, let's start. Good morning. April 1st. That's the joke. Okay, so today we're going to cover the second fundamental theorem of calculus. Even though it looks nasty, I'm going to go ahead and take my time, go through some of the items. Many of the proofs are going to be, so we're going to sort of write a certain proof, but the same proof is going to work for multiple items, and some of the items sort of imply each other and stuff. After we're done with this, and I don't think it's going to take that much time, because there's one sort of contentious part here, which is this item 4. All the rest we can actually do at this point. Probably item 4 I'm going to leave as a problem in the next problem set. After this, we're going to look into some baby versions of change of variables formulas and integration by parts formulas. And then once we're done with that, we're going to transition to Taylor approximation. I want to define at the very least Taylor polynomials and Taylor remainders. Okay. As usual, the standing assumption is that I is a non-empty open interval. And we have this family of functions, which I call this cocycle. Okay, that's the definition of a cocycle. If I have, for instance, a locally hk integrable function, lowercase f, on my interval I, and if I were to choose a base point from a differential equations perspective, this gamma is the initial condition. Well, for each gamma, I have one function like this. Namely, you take an x and send it to the integral of lowercase f from the initial condition gamma all the way up to x according to hk. Okay? And instead of starting with hk, locally hk integrable functions, you can start with Bourbaki integrable, Riemann integrable, whatever. And you can just consider, likewise, the cocycle given by the integration theory that you're thinking of. And what is the cocycle property? It's this very intuitive idea that integration should distribute over intervals. In other words, this should hold, no matter what your integration theory is. Okay, we didn't prove this in class. It's rather tedious, not very sophisticated, but it's a very important idea. Shows up all over math. Okay. The point here is that why, so this is the cocycle identity. So here you have 3 points, A, B, C, like this maybe. And so a cycle is something like this. You start here, and then you go there, and then you go there, and then you return. Whenever you have something like a loop like this, that's called a cycle. Okay? A cocycle is something that zeroes out over cycles. Okay? That's sort of the general idea. And that's why I'm calling this the cocycle. Not that it matters what it's called, but never mind. So, second fundamental theorem of calculus is all about differentiating an integral. An integral in this sense means integrating this cocycle, differentiating this cocycle. So, there are 10 items here, okay? But you want to think of them in 3 different classes like so. In the first class, 1 to 4, you take a local integrable function, lowercase f, and some initial condition, and then you're looking at these uppercase f cocycle functions, according to Bourbaki, Riemann, HK. It says ultimately that the uppercase f is local Lipschitz. In other words, it's weakly differentiable in the weak sense. That's for Bourbaki integrable, Riemann integrable 2. The consequence is the same. Uppercase f is weakly differentiable. For 3, it doesn't suffice that you start with a locally HK integrable function. You need to also assume that the function that you're starting with is locally bounded. Then you can again conclude that uppercase f is weakly differentiable. Still, if you just look at a locally integrable function according to HK, uppercase f is not necessarily going to be local Lipschitz, but at the very least, it's going to be continuous. Okay? So these are general properties. If I have integrability for lowercase f, uppercase f is going to be automatically either weakly differentiable or at least continuous. That's what this says. And you're going to see the proofs of 1, 2, and 3 are going to be pretty much the same. It's just that in the proof, instead of specifying which integration theory I'm using, if I don't specify, it's going to apply to all 3 of them, for instance. 4, it requires something slightly more. Okay? So this 4 requires a nice estimate called the Zach's lemma. Even though it's not very sophisticated as far as I'm concerned, it's somewhat tedious to establish and even write down. So I decided to skip it. So probably you're going to see some version of this in the next problem set. And likewise, you're going to see this 4th item in the next problem set also. Okay. Now the second part, the middle panel, says now more things. It assumes more things. Okay? You start with, for instance, a locally Bourbaki integrable function. You fix an initial condition, gamma, and you fix some of the points, x star. In general, locally Bourbaki doesn't mean your function is continuous, but it could be the case that at this x star, this integrable function is continuous. Whenever you have that, uppercase f is going to be differentiable at the same point, and its derivative is going to be lowercase f. Okay? And likewise, literally the same statement for Riemann integrable functions locally. If lowercase f is good at a point, uppercase f is going to be differentiable. Right? That's how I'm thinking about it. And likewise for HK integrals. If lowercase f is continuous at a point, then uppercase F is going to be differentiable at that point, and it's going to satisfy the differential equation, if you want, at that point. And again, just like the proof that we're going to see for this part, 1 to 3, there's going to be one proof that's going to apply to all three of them. Okay? It's just going to require that you sort of think of what integration means in different senses. But ultimately, we're just going to be using rather general formal properties of integration theories that, I mean, all three of these integration theories have. That's what I'm going to do. These are these. And then the right panel is sort of where everything comes together. We're going to assume if lowercase f is continuous to begin with, well, that means that any one of these apply at any x star. Therefore, uppercase f is going to be differentiable at every point, and its derivative is going to be lowercase f at any point. But if that is the case, I'm saying that this is a differentiable function whose derivative is a continuous function. In other words, I'm saying that capital F is C1, continuously differentiable. Okay? So you see, this is like a consequence of these parts. But in applications and stuff like that, it's good to have sort of condensed statements. Which consequently also means that any continuous function, you see, has an antiderivative. If you start with a continuous function, any of these uppercase f's is going to be an antiderivative of f, which means that C0 space is inside Newton integrable space. Okay. So for instance, in FTC1, we didn't quite have this. We looked at something in the intersection. But now we can say safely, using FTC2 as part of this FTC2, that C0 automatically implies Newton integrable. Okay. Next, more generally, instead of starting with a continuous function, if you were to start with a Newton integrable function, then again we're going to be able to show that for any gamma, the uppercase f is going to be hk integrable, differentiable. The uppercase f relative to hk is going to be differentiable, and it's going to satisfy the ODE. And then finally, if you start with a higher regularity function, k times differentiable, then uppercase f is going to be k plus 1 times differentiable, and it's going to solve the ODE again. Okay. So in a sense, this part, this panel, is the most sort of application-oriented, as far as I'm concerned, at these initial applications. They sort of work out rather nicely. So this board is more toward like integral calculus. You see, it's like we're not even thinking about continuous points or points where the function is continuous. And this is sort of like the transition. Okay. There's more to say about this, but we'll get there later. Kind of proved the first item yesterday, but I'm going to go ahead and go through everything again, slightly slowly. But before I transition to the proof, are there any questions about this? Yeah.
Is FTC 1 and 2 independent or
No.
dependent
Dependent.
to each other?
Certainly FTC2 is dependent on FTC1. We're going to use FTC1 in certain situations. So for instance, here, we're going to use FTC1. Let me think. Well, let me put it this way. FTC2 is all about starting with some function and trying to come up with an expression for an antiderivative. Okay? In FTC1, at best, we assume that antiderivatives existed. In FTC1, I didn't say anything about blah, 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 and therefore antiderivatives exist. Newton integrability in FTC1 was always a hypothesis.
But you did prove it, isn't it?
No?
We don't have to write down the to know that integral exists.
Which integral?
I mean, from writing out an antiderivative is very difficult.
Sure, but no, it's a different matter though. So if you were to look at the statements in FTC1, I always assumed Newton integrability. And then from there, I concluded certain things. So for instance, we talked about this function, the cardinal sine function. This is sine of x divided by x if x is not 0, 1 if x is 0. Okay? This is a continuous function. In fact, it is analytic. It is C infinity at the very least. You can just say this. This is infinitely differentiable everywhere. But for instance, we don't, so by the end of FTC1, we didn't say anything about an antiderivative of this. What is a function whose derivative is this guy?
But can you do the endpoint minus the starting point of antiderivative? Solve it?
Okay, that's the Achilles heel of Newton integrability. Okay? Just because you start with a Newton integrable function abstractly doesn't mean that you can compute the Newton integral. Because to compute the Newton integral, you need to be able to compute at least one antiderivative. Yes. I am assuming antiderivatives exist. That doesn't mean that I know a specific antiderivative. That doesn't mean that I have access to it. Okay? Think of it like this. So if you're thinking about an ordinary differential equation or initial value problem, okay, based on general principles, you can conclude just by looking at the forcing function and the shape of your equation, you can conclude that there's a unique solution. But that doesn't mean that you have access to it.
So existence.
And uniqueness, yes.
But you don't know how to write it.
Well, yes, that's the difference between sort of armchair mathematicians and mathematicians in the real world, in a sense. So from a pure math perspective, we often say, oh, this exists, whatever, and that's enough for us. But then mathematicians who are more, applied, or scientists, ask you, tell me what it is, and we say, oh, well, I don't know. I wouldn't be able to tell you. I can assure you that it exists out there somewhere. And in a sense, you can here think of FTC2 in that sense as well. So again, thinking of sort of like a story, you can say FTC1 was all about sort of all these different people that came after Newton trying to impress Newton. They would be like, oh, it's like if this function is integrable according to Newton, it should be integrable according to my theory as well. That's one part. FTC2 is a critique of Newton, in fact. That's how I imagine it. So FTC1 was all about impressing Newton. FTC2 is all about going beyond Newton. Now people are saying, your integration theory is in fact not that useful because it requires that I can guess at least one antiderivative. But now, in FTC2, all these people go ahead and say, in fact, what I can say is, here is a method of approximating a possible antiderivative. Because all of these capital F's here are defined as a limiting procedure. Okay? Which means, for instance, if you were to start with a lowercase f, Newton wouldn't be able to tell you, not necessarily, an exact function, exact antiderivative. If you were to tell to Newton, give me the capital F for this. He may not be able to do that. But any one of these theories, in fact, implicitly give you a method to approximate a possible antiderivative.
Is it as long as you give me an epsilon, I'll give you
Yes, yes. But epsilon can be arbitrarily small. Epsilon can be arbitrarily small. That's the point. Yes. Yeah, I mean, that's the power of mathematical notation. So it's like underneath this expression, there's like 7 different limits that sort of like do a bunch of things. Like there's a gauge, and you take like sample partitions, you look at the Riemann sums, whatever. But we've seen how nasty of a thing this is. In Calc 1, this is like an algebraic expression. But now we know there's like a bunch of like nasty stuff underneath. But that nasty stuff also tells you a way to approximate things. Okay? Any other comments or questions? So in a previous problem set, for instance, I gave you this problem where I gave you an epsilon, and I asked you to compute the Riemann sum up to a certain degree, whatever. So that would be an approximation. Like, there's like an advanced version of this course where we also think about the sort of estimates rather more carefully. But this is the first class, and even though I sort of kind of mentioned some methods people use, we're just like being rather pure. Our approach is rather pure. Some of you are going to go into applied fields, and then it's going to get a lot more nasty, the estimates and stuff. Any other comments or questions? So, proof of 1, 2, and 3, okay? The same statement is going to apply to all 3 of them insofar as you interpret the integral accordingly. You can also say 3 implies 2 implies 1, whatever, 2, but the point is this, okay? Locally Bourbaki integrable or locally Riemann integrable means these functions are integrable on each closed and bounded interval. But we know that Bourbaki integrable on a closed and bounded interval implies bounded. Therefore, B log and R log are automatically in FB log. I'll write it like this. Oh. Okay. And you see, that's what I'm going to use ultimately. That these functions I'm trying to integrate are locally bounded. These 2 hypotheses imply immediately that the function I'm trying to integrate is locally bounded. For HK integrability, I don't have necessarily local boundedness, and therefore I need to take this intersection. Okay? That's the difference between 3 and 4. So, let f be integrable, locally integrable, let's say, according to whichever theory, 1, 2, or 3. Be locally integrable. I take a base point or initial condition, gamma, and x star is going to be in I. Okay. So what am I trying to do? I'm trying to bound the distance between this and this. Ultimately, this is what I'm trying to get. For uppercase F to be locally Lipschitz for H small. Okay? But since in either one of these three cases, f is locally bounded, well, there is a delta such that on the open interval, or maybe closed interval also, on the closed interval centered at x star of radius 2 delta, or 1 delta, f is bounded, and so I can just use that. Since f is locally bounded, there's a delta positive, and there's a, say, c positive, such that for any x in I, if x minus x star in absolute value is less than or equal to delta, then f of x in absolute value is bounded by c, maybe like this. That's what it means for f to be locally bounded. Ultimately, the idea is to integrate both of these sides. The only problem is that just because lowercase f is integrable, in general, I don't know that its absolute value is integrable because I want my statement to hold for hk also. Therefore, instead of applying integrals to this, I'm just going to do a little trick, and I'm going to apply integrals to this. Okay? Certainly, Bourbaki integrals, Riemann integrals, and hk integrals are all monotonous. In other words, if you have three functions like this, you can integrate all three of them, and the integrals are going to have the same inequalities. And so if I were to integrate, here I get minus c times h. Here, x star to x star plus h, f of x dx. And then here I'm going to get ch for h less than delta. But then if this is the case, this is a number that is bounded by something like this and something like this. This is the same thing as saying that this integral is upper bounded by c times h in absolute value. But this is nothing but by the cocycle identity, f sub gamma of x star plus h minus f sub gamma of x star in absolute value. So I was able to show for any x star, there is a delta and there is a constant such that if h is bounded by delta, then the image of x star plus h and x star under capital F is upper bounded by the distance between these two, which is just h. That's what it means for capital F sub gamma to be locally Lipschitz. This was also the proof that I had written yesterday. So as you see, it's not that sophisticated at this stage. We just write down. We just use like standard rules for integrals. Okay? Mm-hmm.
Can you repeat? If we have a function that is locally bounded
Yes.
and integral,
Yes.
we will have that.
Yes.
We can integrate.
Mm-hmm.
So we start out with a function that is locally bounded.
Yeah. So think of it like this. So in the first case, the hypothesis is f is locally Bourbaki. Okay? And I fix a gamma. I want to show that capital F sub b. So when I'm going to look at this integral, I mean integral in the sense of Bourbaki. Okay? Locally, I'll write it like this. T integrable here's integration according to t. T, integration according to t, integration according to t. All this works for t in B, R, L, or HK. I didn't write this, but
Finish the proof.
yes, yes. So all these properties, the only properties I used were properties that all three of these integration theories had. So I was not biased toward using one integration theory here, which means what I wrote actually applies for all three of them.
Lipschitz, locally Lipschitz.
Yes.
By differentiability.
No. That's why there's a next step here. But you can still talk about this uppercase f as a function in and of itself. And local Lipschitz, at the very least, is differentiable in the weak sense. Okay? Any other comments? This is where the story starts, actually. It's like there's more to say about all this, but I don't want to go any further. So that's the proof of 1, 2, 3. Proof of 5, 6, 7. Again, I'm going to write something that's going to apply to all three of them simultaneously. The point here is that even though these integration theories are sort of separate, they have different flavors, whatever, insofar as I stick to certain formal properties of these integration theories, like these, then whatever I write will be agnostic in terms of the specific integration theory I'm using. OK. 5, 6, 7. So now I'm assuming that f is continuous at x star. And I need to show that uppercase f is differentiable at x star, with the derivative being lowercase f at that point. OK? Again, I'm assuming that lowercase f is locally integrable. And I'm assuming that at least at x star, it is continuous. So somehow I'm going to need to use this property of lowercase f. So for any epsilon, there is a delta, blah, blah, blah. Right? Well, maybe let's write it down. What does it mean for lowercase f to be continuous at x star? That means that for any epsilon, there is a delta such that for any x in I, if x minus x star is bounded by delta, then f of x minus f of x star in absolute value is going to be bounded by epsilon. Okay, this I'm assuming. Based on this, I want to show that uppercase f is differentiable at x star, and its derivative is lowercase f. Okay. Well, what do I need to control? We need to control something like this. I'll write it here. So, well, I'll just write it like this. I want this. right? So this should be this. Like so. Up to higher order terms, capital F at x star plus h should be capital F at x star plus this constant, oh, should be like this constant times h plus higher order terms. That's what that means. In other words, rearranging, I'm trying to control this expression. Minus I'm trying to control this as something that decays faster than h does, as h goes to 0. Okay? Opening this up, again, I can flip the orders of these. That gives me a plus. And then this part just becomes capital F sub x star at x star plus h. And then this becomes this. This is the integral of lowercase f from x star to x star plus h. The only trick here is that you want to think of this as an integral as well. You think of this as a constant function integrated over the same domain. Okay? So you can write it like so. So to control this, all I need to do is to control this. X star is constant. It's inside the integral, but it's a constant, okay? And I split this. This part is going to give me f of x star times h. And then here I'm going to have the integral of lowercase f from x star to x star plus h, which is going to give me this cocycle part. Okay. But the point here is that because I have continuity of f at x star, for h small, I have a bound over this. That's what I'm going to use. Okay. So this, again, instead of integrating this, I'm just going to expand. And I'm going to say that f of x minus f of x star is upper bounded by epsilon and lower bounded by minus epsilon. Okay, integrate this integral of this dx from x star to x star plus h is upper bounded by epsilon times h, here lower bounded by epsilon times minus epsilon times h. Again, this means that this whole thing in absolute value is upper bounded. By epsilon times h. Okay? But this is this, which is this, which is this. And that was something that I was trying to bound by epsilon times lowercase h. And therefore, that's the end of the proof. It almost feels like I'm cheating. Yeah. FTC1 was a lot more nasty, the proof of it. Even though it wasn't that nasty, actually. It was a rather straightforward idea. But we're not using much, as you see, in FTC2. Any comments or questions? Okay, we proved 1 through 3. I didn't prove 4. That's going to show up in the next problem set. We proved 5, 6, 7, 8. Well, 8 is implied by any one of these, because C0 implies any one of these. So you can just apply. Let's do 9. I think I'll leave 10 to you too. 10 you can prove by taking 8 and doing induction, I'm going to do 9. Okay, I'll write this. So remark. 5, 6, 7. Any one of these implies this. And then I'm going to leave this to you as an exercise. This implies this, and vice versa, by induction. I want to prove 9. So I start with 9. I start for 9 with a Newton integrable function. In other words, I have a lowercase f that I know has an antiderivative. Okay? So there's at least one differentiable function, uppercase f, such that its derivative is lowercase f. That's what it means for lowercase f to be Newton integrable. Now I need to show that somehow this is differentiable. Okay, that's a different function. Okay. So here's a trick, okay? Look at this. I should also mention, just to remind you, remember from FTC1, we showed that Newton integrability implies HK integrability. So because I start with a Newton integrable function, I can safely think about this cocycle, HK cocycle, but not necessarily Riemann cocycle. That may not exist in general. But this always exists by FTC1. But what is this? This is the integral from gamma to x of f according to hk. But by FTC1, I know that I can replace this hk by n. This is FTC1. But since I have an antiderivative, capital F, I know what this should mean. This should mean capital F of x minus capital F of gamma. But then I'm just telling you that this hk cocycle with initial condition gamma is equal to the function that is capital F minus a constant. In other words, this function is a linear combination, or a differentiable function up to a constant. In other words, this itself is differentiable, and its derivative is the same thing as the derivative of this, which is the same thing as lowercase f. Which is the end. So somehow 9 says this, okay? If you know that lowercase f has at least one antiderivative, using this HK integral method, you can approximate some antiderivative. Not necessarily the original one, because this is not necessarily equal to this, but up to some constant, you can approximate one antiderivative. That's pretty nice. Okay? And that's the end of the story, at least for us. Now, going further, I want to say a couple of words. To go further, you need to sort of really understand this Lebesgue paradigm. But for instance, it turns out to be the case that if you start with, say, a Riemann integrable function, or let's say HK integrable function, Oh, I'll just say this actually. Just put here optimism. Okay. If you start with a Riemann integrable function locally, then we have that this guy is local Lipschitz by FTC2. And by one part of it, it also says that at each point where lowercase f is continuous, this guy is differentiable. Okay? But in fact, it turns out that the only functions that are Riemann integrable are functions that are continuous almost surely. So they are continuous pretty much at every x point, every input point, which means these weakly differentiable functions are differentiable almost surely. So if you were to choose a random point, x star, and if you were to try to compute the derivative, you're going to be able to compute the derivative. Okay? In fact, f is C0 almost surely. That is to say, if you were to take a random point on the interval, at that point the function is going to be continuous. Okay? And therefore, again by FTC2, this uppercase f is going to be differentiable almost surely. So in fact, you're able to solve this ordinary differential equation at pretty much every point. Not everywhere, but almost everywhere you get to solve it. Okay? And so many of the things that we've been discussing, for instance, the distinction between uniform convergence and pointwise convergence for sequences of functions, there are also sort of versions like this. Okay? Once something doesn't work, you say, okay, instead of asking whatever to work everywhere, what if I were to say, what if I were to ask, I want this property to hold at most points? Then the story continues, okay? It's a wonderful thing. And I wrote a reference here. So for those of you who are interested in these kind of things, this is like an advanced textbook, but in the same sort of philosophy, I think something to, I wanted to recommend this. It's by Bartol, A Modern Theory of Integration. For more optimistic results, you need to have a look at that. Now that's a graduate level textbook, so it's not as straightforward, but still. For more. So he discusses all these sort of generalized derivatives or weak derivatives, weak differentiability, and all that stuff, or weak antiderivatives and so on, and a bunch of variations on the fundamental theorem also. I really liked the approach. Okay. Again, like I said, this is more advanced, but it sort of develops HK integrals, Lebesgue integrals, all these things simultaneously. I wasn't aware of this textbook, but eventually I sort of came across it. And the exposition here is very similar to the exposition I gave, but at a more advanced level. Are we out of time? OK. Well, we didn't get to continue, but we're going to do by parts and change of variables tomorrow. Thank you. Not tomorrow, I guess on Friday. All right, let's start. Good morning. So today I want to discuss one rather simple version of u-substitution. In other words, change of variables formula for integrals. And then again, one rather simple version of integration by parts formula. Now these are rather important rules, and indeed you can just take either one of these, and like by keeping generalizing them, you can just obtain rather important results and generalizations. But since we're short on time, I thought I would just fast forward these two things. You can have a look at the Bartle book that I mentioned last time. In that book, there's a bunch of generalizations of this, and you can sort of look into other places as well. So the reason why I'm going to just state the baby versions of these is so that we can move forward. And I think we spent plenty of time with the first fundamental theorem of calculus, second fundamental theorem of calculus. Those are certainly a lot more important than these. So, and then once we're done with these, we're going to finally do Taylor approximation. And that will be it for the second part of the course, let's say. And then next week, we're going to transition to infinite sums, which is going to be the last topic. So the way I think about it is that baby u-substitution formulas are essentially integral calculus versions of chain rule. And integration by parts formulas is nothing but product rule for integral calculus. Okay. So instead of going in the forward direction, namely first stating the theorems and then proving them, we're going to try to do something slightly different. We're going to try to be rather cheap. And so we're going to look and see what we can prove given the things that we have proved so far. And then after we do a bunch of things, we're going to state the theorem that we proved. Okay, that's also a method that, in certain circumstances ends up being useful. So you would start sort of reading something page after page, and then eventually it would end with a theorem. They would say, oh, we just proved this. You didn't know that I was proving something. I was actually proving something. OK, so I don't want to look into the hypotheses, whatever. Obviously, I'm going to assume some sort of differentiability. But beyond that, I don't really care that much about. So I want to start with a chain rule. So say I have one interval like this. Let's first focus on the u-substitution. I'm going to take two intervals, actually. OK, like so. I'm going to compose a bunch of things, right? So chain rule is about composition of functions. Say this interval is I, this interval is j, this is the whole reals. Say I have a function like this, and then I have a function like this. So what I'm trying to say here is that, say I'm trying to integrate f. Say perhaps this is the situation. Say from 1 to 2, sine of x squared, and then I want to say u equals x squared, for instance, here, which means u prime should be somewhere here. Okay. Imagine we have this integral. Okay. And of course, I hope you would agree, if you were to see something like this, your first instinct should be u equals x squared. That should be the substitution. Okay, and then you're going to say, oh, if that is the case, du equals 2x dx. Okay, so you can sort of do the substitution. We haven't developed a formalism for this. This is what is called the differential form. Those of you who are going to take the second class, if the instructor likes it, are going to study this. Last semester, when I taught 30 to 20, I did spend about a month discussing differential forms, but it depends on the instructor. So essentially, this is what we're going to try to do, but ultimately, I don't want to use this formalism. here I'm going to, for instance, say f of, say, y equals sine of y. Okay. And then phi of x is going to be x squared, for instance. Okay. Is that what I want to say? The orders kind of get confusing here. Let me think. This is the one side. Right. OK. So if I were to use this formalism, OK, this integral becomes 1 to 2 f composed with phi of x and then phi prime of x dx. OK. OK. But then u-substitution, like so, should tell me that this is the same thing as sine of u du, where u varies from 1 to 4. Right, so this is the Calc 1 approach. This is sort of the type of formula I'm trying to get here. And so, in practice, this looks more complicated. And then you turn it into this. And in our formalism, then this is nothing but f of u, and maybe I should say y, f of y dy. And then what are the endpoints? Phi of 1 and phi of 2. Okay, so this should be my formula. Okay, and so based on this, I'm going to try to apply the chain rule to this, the composition, and get something out of it. Well, I can't quite necessarily apply chain rule to lowercase f, but let's say it has an antiderivative, right? Because I want something whose derivative is this function. I want this to be the outcome of something. So say lowercase f is Newton integrable. So there's a capital F such that capital F prime equals lowercase f. That's what it means for lowercase f to be Newton integrable. And remember from FTC1, Newton integrable implies locally hk. So I can integrate this too according to one of these integrability things. And so if I were to apply to capital F composed with phi, say this is also smooth, differentiable. Okay. If I were to take this composition function, this capital F is defined on the same interval. Right? If I were to differentiate this at x, what is this? This is capital F composed with phi times phi prime at x. But capital F prime is lowercase f. So I have this, okay, which is exactly this side of the formula. And so that means that, how to write it? Say I take 2 points in I, send them to j using my phi function, my change of coordinates function. And so the integral of lowercase f on this interval then should be the same thing as the integral of the composition function on this interval multiplied by this correction factor. So this is sort of the idea. And so I can say something like this, for instance. Let lowercase f be Newton integrable on J, taking real values. And let me let phi to be a diffeomorphism. You don't need the diffeomorphism, but I don't want to worry about like inverses, whatever. I can just assume that it is differentiable. Its inverse is also differentiable. That goes from I to J. Okay. Well, you see, by virtue of the fact that this function I'm trying to integrate, this, is the derivative of some function, that means that this function would be Newton integrable, hence locally HK integrable, and the integrals should match. Then on I, and for any alpha, beta in I, we have this. This in the sense of HK of f of y, dy equals, again in the sense of HK, alpha to beta, f composed with phi of x, phi prime of x, dx. Okay. Let me try to formalize this just a little bit. Proof of this, okay? Now, I'm assuming that lowercase f is Newton integrable. So there is a capital F such that capital F prime is lowercase f. Now I can start from here, and I can say y. By the first fundamental theorem of calculus, the HK integral of lowercase f is the same thing as the Newton integral, which I can evaluate using this uppercase f. So I need to plug in this endpoint into f and subtract from it f applied to this fundamental theorem. But of course, this is nothing but capital F composed with phi applied to beta. That's how we define composition of functions. And likewise here. But then, since capital F is differentiable, and so is capital phi, well, this composition is differentiable. And it is an antiderivative of its derivative. Meaning, this is the HK integral from alpha to beta of capital F composed with phi prime of x dx. But then by chain rule, this is exactly this. Which is what I wanted to prove. Okay. Any comments or questions about this? Yeah.
The final one,
Yeah.
f composed with phi x,
Yes.
that's the chain rule on what? F1?
No, no. I'm saying this function multiplied by this
Right.
is the derivative of capital F composed with phi.
Right.
So that's where I use the chain rule.
And what was you trying to prove?
I was trying to prove that this is equal to this. this is equal to this. So I applied FTC1 here and FTC1 again here. That's two applications of FTC1. And here I use chain rule. Okay. Make sense? Okay. But you see, I also want to mention, it's like at this point, we're really going back to Calc 1. It's like we're just basically doing algebra but with derivatives and integrals. Like there is stuff underneath, and if it comes to it, you open it up, do things. But in pure math, often you sort of prove one big thing, and then you sort of keep farming that result to get more and more things that are convenient in terms of calculations. OK, so that was u-substitution. How about by parts? Well, by parts is about this issue of integrals not distributing over products, right? So that was the whole thing. So if I have fg like this, we talked about how this in general is not the same thing as the product of the integrals. And the fact that this is not the same thing as this in general is so important that their difference, this difference, this, shows up all over the place. And I kind of mentioned how, for instance, in probability statistics, you think of functions as random variables. And this product random variable is, well, it represents two events happening simultaneously. Okay? This integral then becomes the expectation. What is the probability of me wearing these pants and this shirt today? Okay? On the other hand, this is the probability of wearing these pants by itself, and likewise this, me wearing this shirt, the probability of me wearing this shirt. And so when you look at the difference between these two, well, either it can be 0 or it could be non-zero. If this were equal to this, that would signify that these two random variables are independent. So there is no correlation between me wearing these pants and this shirt today. Often that is not possible really, and correlation is like approximately 0 or whatever, but it ends up being useful. And so because you don't have something like this, you still would like to be able to differentiate, or rather integrate something like this. At large, you cannot quite necessarily do this, but by parts tell you that if one of these is Newton integrable, then you can say things. Okay? If one of these functions were dv of dv form, let's say, and so this is the Calc 1 notation, equals uv minus v du. What does this say in our notation, or in our terminology? It says this guy is integrable, or rather, this product is integrable. But to say the least, this is a Newton integrable function. And so is this. And so based on this, I want to start with two Newton integrable functions and try to sort of rewind the product rule. Instead of uv whatever, I'm going to use a and b. So say you have one function differentiable, capital A. When you differentiate, you get lowercase a. And then another function, capital B, that when you differentiate, you get lowercase b. Okay? Well, if that is the case, when I differentiate a times b, what do I get? I get a prime times b plus a b prime, which is the same thing as lowercase a times b plus capital A times lowercase b. Yeah, this is just a product rule. Now, what else can we say? If that is the case, this guy is Newton integrable. It has an antiderivative. And so is this. And so is this. You see, this is the derivative of this. Now, for me to be able to say something about the integral of this guy, in terms of the integral of this, I need to actually assume that this guy is hk integrable. I could say that, so for instance, you can start with a function that is not hk integrable, and there are functions like that. And then you can just try to engineer something that is the negative of this, so that ultimately here you would end up with a 0, but neither one of these pieces are integrable. These are technical matters, but it's a problem. So what I can still assume is, this guy is hk integrable if and only if this is. And in that case, I have the by parts formula. So what I can say is something like this. Let AB be Newton integrable on I, and capital A and capital B be two antiderivatives. Be antiderivatives of lowercase a and lowercase b. Of a and b, respectively. Then this is hk integrable if and only if this is. And in that case, I have the u-sub formula. This part is integrable if and only if this part is integrable. And if the first item holds, so let's say if AB is hk log, then we have the formula for any alpha and beta in I, integral, according to hk, from alpha to beta of, maybe I'll write it like this, equals, well, I'll use the variables too. This is equal to capital A times capital B evaluated at the endpoints minus the other way around. And here's a short proof of this. Well, the first part we already proved by this consideration. We just need to prove the formula. I have this, right? And I know since, let me put it this way. When I write this, I mean AB evaluated at beta minus AB evaluated at alpha. Which is the Newton integral of the derivative of AB. By definition. But then by FTC1, I know that instead of n, I can replace it by hk. And then expanding this product rule gives me what I need. because I know that I can distribute integrals over sums of functions. I'll write it like this. This is by definition, this is by definition, this is FTC1, this is product rule. And taking this to the other side gives me that this is equal to this minus this, which is what I wanted. Okay. Pretty nice. Comments or questions about this? I'll say one thing about by parts. Looks like it's such a convenient thing, and it is, but it's also very deep too. Because if you look at this formula, how to say? In a sense, if you allow yourself to differentiate functions not by themselves, but at least under integrals, say you're looking at an expression like this, lowercase a times uppercase b. In this version, we're assuming that uppercase b is differentiable. Okay? It's an antiderivative. But say it's not differentiable. And there is some lowercase b such that it fits to the right-hand side. Using that, you can in fact define some notion of differentiability for an uppercase b by just using this right-hand side, insofar as you can find some function, lowercase b, such that this works. So this leads to this is the sort of first introduction of what is called the weak derivatives. You sort of differentiate under integrals by using by parts. You sort of generalize everything in such a way that integration by parts still holds in a generalized sense. So that's pretty nice. But I don't want to say anything further because it's more advanced. Okay. Any comments or questions about either one of these? And how do I remember these? Like this. Whatever u sub is, it should be basically like chain rule. Whatever by parts is, it should be pretty much product rule. Okay. Now I want to transition to Taylor approximation. If you look at the textbook, this is the last topic in the textbook, but I think it's kind of backwards. So we're going to use Taylor approximation first, and then we're going to keep the degree of the Taylor approximation larger and larger, and that's going to lead to analytic functions. Taylor first starts with infinite series and then goes back to Taylor approximation, which to me is not as smooth of a transition. So now I want to take n, a non-negative number, a function that is n times differentiable. I should have said definition here. And let me take a base point. Then I want to associate to this lowercase f a polynomial. We in fact did this even for 1 times differentiable functions. In the case of once differentiable functions, we associated to f at x star a degree 1 polynomial, which was f of x star plus f prime of x star times something. I want to do something like that, but using also the higher order derivatives. Then the order n Taylor polynomial of f at x star is this. It's a function that is a polynomial. It depends on these things. From reals, it goes to reals. That takes an x and sends it to this. Okay. I'll do an example in a second. This is one notation. Sometimes it becomes more convenient to call this h, do a change of variables. And so you can write it like this as well. Okay? These are the same things. Now, even though, you see, this function, this polynomial, is defined everywhere, of course, what we're going to ask is that this be approximately f near x star. In which sense approximate? We're going to ask that this is order n tangent to it. Just like with first derivative, we were asking the tangent line for n equals 2, for instance. We would ask for the tangent parabola. N equals 3, we would ask for the tangent cubic or whatever. This is the order n Taylor polynomial. One thing that's going to be important for us also is the difference between the polynomial and the function itself. That's called the Taylor remainder. The nth Taylor remainder of f at x star is, well, I'll write it here, the function r sub n of f comma x star, which is f minus this, their difference. Of course, you can differentiate a polynomial as many times as you want, but since it is also the case that lowercase f is n times differentiable, the difference of two n times differentiable functions is going to be n times differentiable also. That's going to be important for us. I think I might postpone the proof of Taylor approximation to Monday, because when you first encounter this notation, it's kind of overwhelming. I want to take my time and sort of parse through it. Let's see. Let's do this. I want to first give an example, okay? Say I start with a polynomial to begin with. Certainly, polynomials are n times differentiable for any n at any point. Polynomials are C infinity. In fact, there are more, but at least they are C infinity. And so somehow, these things should apply to a polynomial also. Now, I'm going to do it for a quadratic polynomial, but the same calculations are going to work for higher degree polynomials. It's just that because there's a bunch of indices involved, as far as I'm concerned, index management becomes somewhat overwhelming. So here's an example. Okay, let's choose lowercase f to be a degree 2 polynomial that is arbitrary. Okay. So a0 plus a1x plus a2x squared. Okay. I want to apply these things and compute everything else. So I'll write it here. F is C infinity, infinitely many differentiable. Okay. So for any lowercase n, non-negative integer, I should be able to look at the nth Taylor polynomial of f at any point, and likewise the nth remainder. I'm going to leave x star arbitrary. Okay. Here's what I'll do actually. What I'm going to do is not going to work for arbitrary functions, but for polynomials. In fact, all this Taylor polynomial business, you're going to be able to recover by simply expanding your polynomial at x star plus h. Here's what I mean by this. I'm going to look at this. I'm going to plug in x equals x star plus h, and I'm just going to expand algebraically. Okay? This algebraic expansion is going to produce all these things. And it's going to sort of lead to what the Taylor approximation is trying to achieve. Okay? I'm just plugging these in. Okay? Now I want to expand this. But since in these coordinates, I'm looking for a polynomial in h, I'm going to collect the terms according to the orders of h. Okay? And so I have h to the 0, h to the 1, h to the 2. That's a0. Here I have a1 x star, and then here I have a1. Here I have a2 x star squared. Here I have 2a2, and here I have a2. I just algebraically expanded everything and collected according to the orders of h. Okay? No calculus involved. However, note that this, the coefficient next to h to the 0, is nothing but f at x star. And note that this, oh, I should have put here x star. Okay, now it works. This is nothing but f prime at x star. And this is f double prime. Not quite. There are certain coefficients missing. But what we can say is something like this. The 0th order is certainly f at x star. This is this. I'll compute f prime and f double prime on the side. Here. What is this? 0th order term drops. This is a1 plus 2a2x, which means f prime at x star is a1 plus 2a2x star. Okay, so this is exactly f prime. At x star. And then f double prime is a derivative of this, which is 2a2. So you see, f double prime at x star is not quite a2, but it's up to some constant a2. I can say this. Okay. So this is this. In other words, f of x star plus h is f of x star plus f prime of x star times h plus f double prime of x star divided by 2 times h squared. I just obtained this. Okay, apart from this side, I obtained this rule purely by expanding. Okay? So now I can say this. What is the 0th Taylor polynomial of this polynomial, this function f? Well, it's nothing but this sum where uppercase n, or rather, n is 0. So this is just a 0th order term. So this is a 0th order term. I'm going to delete this. So okay, even though it's a function of x, it's a constant function. It's a degree 0 polynomial. Okay, this is constant in x. What is t1? Well, it's the sum of the first two terms. Write it like this. Okay, 0th order term plus f prime at x star times x minus x star. Instead of h, right, h is the difference. This is a polynomial in x. Okay. And then what is the second Taylor? Is, well, it's the same thing. It's itself. Which is the whole thing. And indeed, if I were to look at T3, I know that the third derivative, fourth derivative, whatever, are always going to be 0 because I started with a degree 2 polynomial, which means that, in fact, what I can say is that the nth Taylor polynomial of this function at any point is the function itself for any n starting from 2. Okay. How about the remainders? Well, the remainder is the difference. I think I'll write it here. I can just erase this. Right, so R sub 0, 0th order remainder is f minus t0. Okay. What is R sub 1? Oh. Well, f minus t sub 1, which is this, okay, what is R sub 2, or R sub n for any n at least 2? F of x minus f of x, which is 0. Okay. Any comments about this? Now, these are the calculations, but I hope you would agree with me that these right-hand sides, in other words, expressions, explicit expressions for remainders, are significant for us. R sub 0 is about continuity. I would want R sub 0 to go to 0 as x goes to x0. That would mean for me that f is continuous. R sub 1 is about differentiability. I would want this expression to go to 0 as x goes to x star. But not only that it goes to 0, but in fact it goes to 0 faster than x does to x0, or x star. And you see, in this case, because we had started with an algebraic function to begin with of order at most 2, well, second remainder, third remainder, all of these vanished, which means we were on the nose getting what we wanted. Now, Taylor approximation, you see, applies to a function that is not necessarily a polynomial. Okay? I think I want to do one more example. Let's think about the sine function. Remember, the sine function, or its approximation, we kind of talked about. We said that for small x, or small theta, so f from r to r, theta to sine of theta, one of the very important approximations is that f of theta, or sine of theta, is approximately theta for small theta. That allows you to, for instance, transform the nonlinear pendulum to a linear pendulum. So it's very useful. But the benefit of this, and why, in fact, it works in the context of the second order ODE, because ultimately the oscillation formula comes from f equals ma. A is double prime, which is acceleration, which means I cannot just look at the first order approximation. What it is that the reason why this works is because this is also the second order approximation. Okay? This is a second Taylor polynomial of sine at 0. Cosine. So f prime at 0 is 1. F double prime of theta is minus sine. So f double prime at 0 is 0. So the second Taylor polynomial of sine at 0 is f of 0, 0. So I'll write it like this. Or I should say probably theta here. Like this, and then f double prime, 0 divided by 2 times theta squared. That is to say, pretending that sine of theta is a second order approximation, and that is why it works in the oscillation equation. Okay? We still haven't proved that this approximates sine up to second order, but Taylor approximation is all about this. So you see, the reason is that many functions in calculus, in applications, are not even polynomials, okay? They're not even C infinity, but never mind. At least they're infinitely differentiable. Taylor approximation allows you to just truncate some higher order terms, depending on the situation, and just pretend that the functions that you're dealing with are just polynomials. So this is a very powerful thing. Okay? Both in pure math and in a lot of applications. And so when people talk about up to first order, this is this, whatever, they're talking about Taylor approximations underneath. Okay? Very good. We haven't stated the Taylor approximation theorem, but I think I'm going to do that on Monday. Thank you.